Hey YouTube, in this video we're going to be discussing how to use the definition of the derivative in order to find, say, the slope of a graph. And in this particular case we're going to say the graph of y equals x squared at a couple of given points here. So let's say the point 1, 1, which is on the graph, and we can easily verify that, but that's on the graph, and so is the point 2, 4. I also like to bring up the fact that the point negative 2, 4 is also on the graph while we're here. But we're going to do this using the definition of the limit. So let's go ahead and start with this. When we talk about the derivative of a graph at a given x value, what we're saying is find the slope of the graph at that given x value. So what I've done was I've already constructed a graph of this y equals x squared, and you'll notice that I've got a point A here. And the interesting thing is that I've already got a line, or a tangent line specifically, going through this point A. But recall that the slope of our graph at any given point, say this point A, would be equal to, or the exact same thing to, the slope of the tangent line to the graph at that point. So when we say at the point 1, 1, let's go ahead and drop A on the point 1, 1 here. And we said, well, we could probably estimate the slope of this line, this orange line. You know, rise over run looks to me like it hits at like 2, 3. So really it went like up 2 over 1. So we can say the slope of my graph at x equals 1 is roughly 2 over 1, or just 2. We're actually going to discover that it is exactly 2, but we want to do this formally with a definition of the derivative. So let's go ahead and bring that up. We say the definition of the derivative is equal to this. We say the limit as h goes to 0 of this quantity, f of x plus h minus f of x all over h. Okay. So we say as h gets smaller and smaller here, this represents the slope of the secant line of our graph, but that secant line, as h gets smaller and smaller, approaches the tangent line. And so we say this is really the derivative here. So we're actually going to find this. So one suggestion I can give before we start is this. You know, it's helpful to maybe find f of x plus h off to the side somewhere. So out of all the values here, f of x, we seem to already know f of x. F of x is equal to x squared from above is our function. Okay. H is equal to h, so we say h is equal to h, but f of x plus h, this quantity we need to plug in. Now recall that when you have a function, whatever you plug into that function, whatever you saw in x previously, you have to plug in the value that I've just underlined here. So we say if f of x equals x squared, then f of x plus h equals x plus h squared. And so if we FOIL this out, we actually get x squared plus 2xh plus h squared. And so these quantities are the ones that we shall be using over here on the left. But we say in order to find the derivative of this, it would be equal to the limit as h goes to 0 of this. So now we said f of x plus h, which is this quantity here. So we'd say x squared plus 2xh plus h squared. So this is our f of x plus h. So now we are going to take off, subtract f of x, and f of x here was just x squared. And this is all over h, because h was h from above. Okay. So anyways, sorry, I just keep with the color scheme here. H was h from above. Anyways, now that we've got these all plugged in, I just want to bring a few things up here. We say the limit as h goes to 0. You're going to notice some things when you evaluate derivatives. Starting with this, the top often simplifies. So we end up with here the limit as h goes to 0. You'll notice that we had x squared plus 2xh plus h squared minus x squared. So these x squareds here cancel each other out, and the quantity we have left on top is just this 2xh plus h squared all over h. Now you notice if we try to direct substitute this 0 in for all these h's right here, we actually end up with 0 over 0, which is indeterminate form, and we don't want this. What we're going to have to use is some technique that you might have learned when you evaluate limits, but the dividing out technique. And so basically, let's notice here that we could rewrite this again with the top being factored, where we factor out the h. So we say h times 2x plus h, and this is all over h. And the fact of the matter is this causes our h's to cancel out. And so this limit, after using the dividing out technique, is as h goes to 0, we say the limit of 2x minus h. So now if we said let's direct substitute now, that would mean everywhere I see an h, whoops, almost put it in for x, everywhere I see an h I'm going to plug in 0. So this limit would have to be equal to 2x. And what we're going to do is we're going to give this a name. We're going to call it f prime of x. And f prime of x, okay, is the derivative function. Okay. So now, here's what I want you to realize. The derivative function, first of all, is very general. General in the case that it says, you give me an x value, I'll tell you the slope of your original graph at that x value. So let's recall from up top here. We said we wanted to find the slope of the graph at the point 1, 1. And of course, we drew in this tangent line, drew in the graph, and we said the slope of this line looks to me to be about rises 2, runs 1. But we wanted to prove this algebraically, so here's what we're going to do. We're going to take this f of x here, this function, this f prime of x, the derivative function, and we are going to plug in the x value for which we want to find the slope. Sorry, the wrong key. I wanted this. We say f prime of x equals 2x. So if this is the slope finder function and we want to find the slope when x equals 1, what we're going to do is we're going to say, let's go find f prime of 1. What this is really saying is the slope of graph at x equals 1 is ... And in this case, we get 2 times 1, we get 2. So what this is really saying is, hey, the slope of my graph when x is 1 is equal to 2. And going over here and looking at the picture, we say, yeah, the slope of this orange line here looks like about rises 2, runs 1. So now the other point that we had taken into consideration was this point 24, and as a consequence I said negative 2, 4. But if we were to go and now move our point A over to 2, 4. Now 2, 4 is right here. We say let's find the slope of this line now. So we could do another rise over run analysis here, but we say starting at A, maybe it goes up 1, 2, 3, 4 over 1. So the slope would be like 4. The fact of the matter is, now that we have this derivative function up here, f prime of x, okay, we could say, let's go find f prime of, and we're going to plug in the x value that we want to find the slope at. And the x value now is 2. So we say f prime of 2 is 2 times 2 is 4. And so there's the 4 we should be getting on our picture. And then the last point I wanted to ask about was this one here. We say, how about negative 2, 4? And the reason why I bring this up is because our graph is obviously decreasing here. It's going at a negative rate, or at a negative rate of change, or it has a negative slope. So we would say, well, then this is a lot like 2, 4. If you looked at this, it went down 4, it goes down 4 over 1, this orange line. So the slope of the orange line is about negative 4. But going again back over here, we say, all right, let's find f prime of negative 2, the x value that I want to find the slope of the graph at. So notice we say the x value here is negative 2. Let's plug that into the derivative function, and we get 2x, where in this case, x is negative 2. And you notice we get negative 4. So basically, all of these numbers we keep plugging into the derivative are x values, and all the numbers we get back are slope values of my graph at that x value. So this is an example of how to use the definition of derivative to find the slope of a graph at any x value.